Yeah.
Okay. So there's 3 different mixtilinear incircles here, and you want to show they have a common tangent. Okay, so we pick an arbitrary point L on BC, so it's pretty interesting that L can be arbitrary. And then we want to draw mixtilinear, the L mixtilinear incircles, and then the A mixtilinear incircle of ABC. So, yeah, there's a couple ways. I mean, I could draw all 3 incenters and then perpendiculars, and then, yeah, let me think about the best way to do this. So, I'll just do it one by one like that. There's really 2 different ways to draw I'll just do it like this. Yeah, let's do it all one at a time. So I'd want to draw the perpendicular to AB, let it intersect the sides. And then draw the perpendiculars at those points. I wonder if there's a faster way to do this. Well, I guess I could draw the ray AD. Let me do it like that. So I draw the ray, and then I draw the perpendicular, and then I draw this. Okay. So this should be one of them. And then I will do the same thing again for the other 2 triangles in the problem. So yeah, I'll leave those points there. We're going to want to draw I'll draw the incenter of LAC. I'll do the same idea, draw a ray, draw the perpendicular. This reminds me of when I work at my job. I have to figure out how to do things with the fewest clicks possible. That's what business is all about. You have to figure out how to get things done with as few clicks as possible. So that, well, this is interesting. Are these, okay, they're not concurrent. So that's going to be the center of it. Okay. And then I'll draw the other one. So for A, B, and L. And the same idea. Here's the ray. And then I will draw the perpendicular. And then I will draw this. 1, 2. Wait, what did I just do? Oh yeah, this. And then I will draw this. So we want to show that these 3 circles have a common tangent. Okay. So let's see, when we move L around, looks like they usually have a common tangent. So I'll just draw it just to see. But yeah, so it's true. You can see that common tangent up there, this one. Okay. All right, so that is the problem.
Take the intersection of AL and Mixtilinear Incircle of ABC.
Okay.
It looks like the common tangent goes through that point.
Okay, interesting.
Then we can basically get rid of one circle and show that. Yeah.
No, I don't think the common tangent goes.
Oh.
Yeah, it looked like it. But yeah, I don't think so. I'll just delete this for now, but yeah, we can add it back later if you want. Yeah, it's interesting. This is such a general problem because yeah, L can be, but the thing is LP and LK are always going to pass through those midpoints. So maybe it's worth drawing them. And AG is always going to pass through that midpoint. So wherever we move L, angle QLR is going to be the same. So I guess maybe if we wanted to make it more symmetric, we could show that the X simillicenter of these two circles is the same as what it is for these two. So maybe there's something special about the X simillicenter. Let's see. Is there something special about that point way down there? Let's see. So obviously it's collinear with P and K. Is it collinear with Q and R? No. Oh no, not P and G and K. Oh, wait a sec. They don't have the same, all three circles don't have the same X simillicenter. I got confused. Maybe we could try Monge's theorem somehow. Yeah, what would that look like if we use Monge's theorem? Basically, yeah, Monge's theorem would be like trivial if the three had a common tangent. So yeah. Sorry, I'll make it look like this again. One sec, I'll be right back. All right, thanks for waiting. Yeah, it's interesting. This problem seems so general. It's pretty cool. So yeah, if we hid the incircle for a second, is there anything special? Or not the incircle. If we hid the A mixtilinear incircle, what can we say about these two circles? Can we use Monge's theorem? So yeah, like what if we start with this, this, and this? Okay, so by Monge's theorem, the x-simillicenter of these two lies on this. That's interesting. So if I draw this, and then I would draw this. So basically the common tangent is going to be the line connecting the x-simillicenter of these two and the x-simillicenter of these two. And those lie on this line and this line. So yeah, that's interesting. See how they all concur, but the lines are just so close to each other that it's hard to see that they're even different lines. But so basically ST, the common tangent, yeah. So maybe there's like something special about this triangle right here. Like, yeah, maybe SUV is like a special triangle. So SU passes through T and SJ passes through V. And anything, so U, P, and G are going to be collinear. Yeah, so we could really define things this way. So we could let GP intersect ST at U, and we could let GI intersect SJ at V. And then we want to show UV as the common tangent. I actually like that idea a lot. So
You didn't draw V correctly.
Oh, I didn't draw V correctly?
Yes.
Oh yeah, because J, what is J? I guess, yeah. Whoops, sorry. Didn't want to do that. So this, yeah, this is not right. What is J? Oh, that's the point of, that's the other point of tangent C with the side, not with the circle itself. Okay, so there we go. Now I might have a W. Let's see. So yeah, let's do it that way. Okay, so we let ST intersect GP, and then we let SV intersect GK. And yeah, that doesn't necessarily pass through I, even though I kind of drew it that way. So, and we want to show that UW is tangent to all three circles. We know that U lies on do we know that U is the X similocenter, or do we just know it lies?
U is the similocenter of
These two.
yeah, P and G, like those two circles.
Yeah.
That's by Monge's theorem.
Yeah. Well, by Monge's theorem, we know it lies on ST, but it also has to lie on GP, so therefore it has to be it. Yeah. Okay. Imagine if you're the mathematician D'Alembert. So it's really the Monge D'Alembert's theorem, but we keep leaving out the other guy's name because it's too long. Hopefully he won't be upset with us in his grave. All right. Okay, so we want to show U. We want to show UW is tangent to this guy.
Drawing the, oh, you're already drawing that. So like, maybe we can use this Argus theorem. That looks good. So OG and S, OK and V, and OP and T are linear. Basically, the centers and the tangency points of circles.
Okay, how did I not see that? That makes sense.
And
wait, why aren't these? Oh wait, sorry, not OG and S.
oh, that is not the center. O is not the center. Just yeah. It is the tangency point of one of the mixed linear circles.
Okay, so I should draw in the centers and in the center. So GS, basically I should draw in the center of ABC.
Yeah.
Okay.
I think we can get something really nice with this Argus theorem.
Okay. So Z, G, and S are collinear. And then P, T, and Z, and Z, K, and B. Okay.
Now, you see, we already have U and W, and those are like the intersection of PG and TS and GK and SV.
Mm-hmm.
So those two are very nicely set up for this Argus theorem for triangles PGK and TSV.
Okay.
So if we intersect PK with TV, then we should get that it lies on UV. UW.
Interesting. Okay, so PK with TV. And then that's going to be pretty far away, but that would lie on UW. I think Hakan just mentioned Casey's theorem. So that also sounds kind of interesting. But I think not the Casey's theorem I usually do on my channel, right? Like the other Casey's theorem with a bunch of tangent. I forgot exactly what the other one is. The 4 circles version. I forgot how that works. Okay, so let's see. Is there anything special about this point right here? So it's going to be way over here, A1, and UW and A1 are collinear. So TV and PK. Whoops. So we know that, so yeah, maybe we could try to show that A1W is tangent to this.
Now, actually, I think we can now prove that A1 is the x-simile center of P and K, since we can apply Monge's theorem on those 3 mixtilinear circles.
Okay.
We already have 2 x-simile centers, and x-simile center lies on line PK, the third one. And so basically A1 is the x-simile center of circles P and K.
Okay, so we know A1 is the x-simile center of these 2. Interesting. Because it has to lie on PK, and it also by Monge's theorem, it lies on TB. So yeah, this A1, W, and U are the 3 x-millicenters, right?
Yeah.
Hit the pairwise x-millicenters. Oh yeah, so we could just say they're collinear by Monge's theorem, right? We don't even need the Sargs, right?
But we need the Zargs to show it is on TV.
To show it lies on TB.
Yeah.
Okay. But do we need the Sargs? Because like, let's say I use Monge's theorem on this circle, and this circle, right? So we then TV and the x-millicenter would have to be collinear.
Oh, yeah.
So yeah. So in this case, you could prove it by Monge or Desargues. They're like 2 different ways of doing it. Monge and Desargues are equivalent, at least for this problem. So, wait, now I'm wondering if we've solved it already. Oh, I think not necessarily. Okay, so ST, U lies on ST, W lies on SV, and A1 lies on TV. Do we have like a harmonic conjugation somehow? Because we have, let's see, G, we have this, this. Let me try something here. So TK and PV. Do those concur on AL? No, I don't think so. So basically what this problem says is, I wonder if this has anything to do with being mixtilinear in the circles, or what if I have three random circles that are internally tangent to one circle? If I use Monge's theorem on any three such circles, will I get that the line of Monge's theorem, the line containing those 3 points, is tangent? Is that true for any three circles internally tangent, or do I need this mixtilinear idea?
It's not true for any.
It's not true for any three. Okay.
That would mean that any three circles tangent to another circle have a common tangent. I mean,
Okay.
I doubt that is true.
Okay. All right. Yeah. Thanks for joining this time, Anmol. This is cool. So yeah. Good luck on your assignments. All right. Okay. So yeah, it's not true in general. So is it true whenever angle QLR? Yeah, maybe we could try to use something about that, like, because this is a fixed angle, right? Angle QLR. So I wonder, like, so this point isn't the intersection, but are these points? No, they're not. Okay. Okay, so yeah, we have to show this line as tangent to all three. So yeah, what happens to this line as we vary? Yeah, let's see what happens as we move around point L. Does anything, can we prove it when L is like the midpoint of, like when L is equal to, I wonder if there's a special case of L that we can prove this on. Like if L is the midpoint of arc BC.
So you think moving points works?
The midpoint of arc BC, you can prove it?
No, like the method moving points.
Oh, yeah.
I mean, if we could prove for that, we could prove for others. You say that.
Like it would also be true for point R and point Q, and then the method of moving points maybe would do it.
I mean, I don't know that method, but I'm asking you.
Oh, yeah, I'm not sure. I'm not very good at moving points. Yeah, this looks hard, but I guess you never know. Sometimes it looks hard and then you find the right trick. Well, what we could do, so what if I draw like two of the tangency points and we know, I'm just trying to think about this. We know U, B1, and C1 are collinear. And, or we're defining B1 and C1. And we know U, W, and A1 are collinear. Is there anything special about, let's see, sorry. Okay, I'm gonna go back to the way it was before. This looks kind of hard to me, but I'm kind of surprised we figured out the stuff we already did actually. We could try to calculate. So here's one idea. We could try to calculate the angle that, so let's say I hid this for a second, right? Actually, let me just draw the tangency points. So we could draw this segment, and we could try to find the angle it makes with AL, and then show that that is the same angle that this segment from W makes with AL, which is the same angle that the tangent from A1 to the two circles makes with AL. So yeah, can we calculate the angle between this segment and AL? Because we know that this segment is the reflection of UTS over this. So maybe using.
It isn't.
Oh yeah, you're right. It's not. Maybe drawing these other tangency points might help. So yeah, so even though we don't know for sure that the tangency points exist, let's just draw them in. Maybe we could find out something useful about them. So this would be the other tangency point, would be E1. And this I want to reflect over that. Wait, that doesn't make sense. Okay, let me skip that one. So I'm going to reflect B1 over PK. And so I have E1, F1. So those are the tangents from U and A1. And if I reflect C1 over WG and C1 over UG. So maybe there's something special about E1, F1, G1, and H1. So G1 and H1 all lie on this circle. So is there something special about this? Almost looks like a trapezoid, right? Maybe that's obvious, I'm not sure. But no, it's not a trapezoid. H1, E1, and U are going to be collinear. Also, maybe drawing the insimilar center would help. So anything special I can say? I don't see much that's true. Other than that, those are collinear by definition. All right, I'm going to delete those points. So Is there something special about C1? I think if we could find something special about C1, that would be good. Is there some? What circle it lies on? C1, let's say C1 O G. Is C1 O G? No. C1 ZIK cyclic. Well, then C1 Z. No, that's a coincidence. Wait, this. Wait, I'm confused. C1 OIK. Wait, I think point O and Z got swapped here. So if C1 Z IK, then C1 Z O. Yeah, I didn't think so. They keep swapping. Z is the center of the, oops, the bigger circle. If this could C1B1 equal C1B1, no. I think they're a little bit different there. Yeah. And again, Z and O get swapped.
Maybe we should try to simplify our diagram.
Okay.
Like I thought about like deleting A1 and U and W should stay. And we only want to prove actually that UW is tangent to the biggest Mixtilinear circle of ABC.
So this one.
Yeah.
Would that solve it?
Yeah, since if let's say that it were tangent to that, then as for example, U is the x millicenter of
These two. Yeah.
Yeah. So we basically only need to handle like I think it is a bit easier to handle like that.
Yeah, we don't need A1. I agree. Okay. I'm just gonna hide it instead, just because I like seeing those points. Okay. We want to show UW's tangent to the, this one. So I could hide the other two. Although I need the centers. Yeah, I need their centers, so. But maybe having the center. Yeah, I don't think I want to hide the other two circles. So if UW is tangent to this, so yeah, maybe I could delete Q and R or remove Q and R. I mean, they could be helpful. I'm just not sure. And yeah, I need to use somewhere that the mixtilinear incircles are tangent to BL and CL. So maybe I do want Q and R. So I think TN actually passes through the midpoint of arc BL. I think that was in my video on mixtilinear incircles. And VJ should pass through the midpoint of this arc. Yeah, TO. Let's see. Yeah. So we'd have the midpoint of arc BL and CL. These are collinear. And these are also collinear. And this is an angle bisector. This is an angle bisector. I wonder if UE1 is tangent. No, it's not. Yeah, I don't know if that really helps. E1 and F1. So I'm going to hide them for now. All right, let's try this for 10 more minutes, and then I think I might just try something else just because I'm a little tired. So isn't there something with like, so I think the two centers and the insimillicenter and the exsimillicenter are like in harmonic conjugation, right? Oh, but these two don't have an insimillicenter, so yeah. But these two circles do. Yeah, that's kind of interesting. So let's say we had the insimillicenter of these two circles. So that point, PK and A1 are collinear, and they're in harmonic conjugation. And then maybe we could project through through G onto UW. And so we get that point, A1, WU, and some other point here are in harmonic conjugation. So let's see if there's anything special about that point. So we have this and this. So this point, UW and A1 are in harmonic conjugation. Well, no, because this tangent doesn't go through. We'd have to draw the line through G in that point, and I don't think that's too helpful. Okay. Well, actually, we could let PK intersect AL. That will be the incimillicenter. And then PK, that point, and A1 are in harmonic conjugation. And then, is there something we can project through, like Z? Or maybe S, or SC1 and that point collinear? Okay, I wonder. No, I don't think so. No, they're not collinear. Let's see. Maybe we can use poles and polars with all these tangents. I don't know exactly how, but
Let's go to the next problem. I think we are still far from solving this.
yeah, I agree. So there's this one and this one. I think this one might be a little easier. Let's see. I kind of like this one, actually. We'll do this one. So we have a triangle inscribed in circle O. So we have like a Semidian configuration. And same idea as like the first problem. That's going to be point P. So AP is a Semidian. And we have point O is the center of the circle. And the bisector of angle BAC. So that's going to pass through the midpoint of arc BC, and we want to see where does it intersect this circle. So it intersects, so we have, this point is going to be the midpoint, and this is going to be point E. And then these are collinear, obviously, O, D, and P. Okay, M and N are the midpoint. Okay, so this should be M. So let's make this a line instead. And these will be M and N. This is M. And the circle with diameter BC, which we can draw like this. It intersects, yeah, I don't want to make it look like those are concurring. That's a little better. It intersects segment EN at F. So that's point F. And we want to show the orthocenter of EFM lies on BC.
This looks familiar. I think we did this on some other session.
Oh, really?
Of it.
It does look a little familiar. You want to keep doing it, or you want to try a different one?
We didn't solve it last time.
Okay. So let's try it. That's E, and then the tangents. So yeah, is there any way we can like redefine things? So let's check out that point. Is there anything special about it? All the way over there. We redefine things in a certain way. Let's see. Does, yeah, so this is going to pass through that point. So we could let this intersect the circle at H. And we could let MH intersect it at G, something like that. And then we want to show E is the orthocenter of GFM. So let's, yeah, so there would be like a lot of different points here. Like this would lie on this circle. So yeah, we have to figure out how we want to define things basically. Because we could, one way we could do it is we could try to show that I, F, H, M, and BC are concurrent, right? That's equivalent. That might be easier. And is IFHM cyclic? Yeah, because they're both 90, right? So do we know that both those are 90? So we know FHM is 90. How did we define, do we know that FIM is 90? Can we prove that by Rhine's theorem or something? Because once we prove that, like if we prove this was cyclic, would the radical axis theorem solve it? I think so. We proved this was cyclic. You have HM, yeah, then the radical axis theorem would solve it. I think. Because we would have this, yeah. Okay, so we need, if we show angle FIM is 90, that solves it. We could draw the midpoint of AM, and then we want to show FI is perpendicular to OJ. E and I are orthogonal conjugates. Okay. Interesting. So they have the same pedal circle. BIC plus PEC is 180 plus A. So basically, yeah, we want to show IF is parallel to AN, right? But AN, oh, I think this is just Rimes' theorem because BANC is cyclic, and we want to show, and BIFC is cyclic. In other words, does that mean that IF is parallel to AN just from that? I think it does. Well, because EH times EN is EM times EA. And then, oh no, we would need to show that yeah, I don't know if this is obvious, but if we let this intersect this circle, we would need to show that these points are parallel to HM. Which is the same as saying NA and those 2 points as cyclic. ME times MI is MB squared, which is MD times MN. So NIED is cyclic. I think that's what you're saying, right? And this almost feels like the power ratio lemma, right? Because we have 3 circles that are all coaxial. And so if we apply it to I and F, the ratio of the powers of I with respect to both circles has to be the same as what it is with F. And I wonder if that proves that IF is parallel to AN. So yeah, I think that proves it. I think that solves the problem because IA times IM over what are the two? IA times IM over IE. Oh no, because then I'd have to draw it all the way down there. I don't even remember what I is anymore. circle with diameter BC, F. Oh, it's just where AM intersects this circle. Right? It doesn't seem like it should be that hard to show this perpendicular, but it seems harder than it looks, I guess. I'm still trying to do the power ratio lemma. Let's see. What if instead, yeah, I just don't want to extend this stuff to have to meet this circle, but maybe that is what I should do. So basically, I'm gonna shrink this diagram a little bit, and if I extend these two, so I have this and this, then I want to show I'm going to draw these 2 points. This and this. So we have IA times IM, and then IE times IK. Okay, that doesn't really help that much. I'm sleepy. So we want to show FIHM as cyclic. And yeah, I'm going in circles here. I mean, we could let AN intersect BC because then we get like a harmonic conjugation. I wonder what the angle bisector BIC is. Oh, you know what? I should have thought about this. Since this is cyclic, IJ bisects angle BIC. And so we want to show that IB, IJ, IC, and IF are in harmonic conjugation. But we know that AB, AM, AC, and AN are in harmonic conjugation. So So, oh no, not, well, that's not totally true. Because angle FIM, we want to show it's 90, not this angle. I almost feel like I want to redefine F to be the perpendicular from I to AM and seeing where it meets the circle. I feel like if I did that, then we would know IF is parallel to AN. Yeah, I'm not sure. What if I'm going to draw AN and I'm going to draw IF and see where they meet BC. And I wonder if there's any kind of relationship there. So we have this point and this point. Sorry. I don't think L is the midpoint of K. LH, okay, so but we want to show LH and M are collinear. That's kind of the whole point. Is KJ parallel to those? It almost looks like it is, but I don't think it is. I'll just use this. I don't think it's parallel because it looks right. No, it's not. I guess the whole reason I did this is because these would be a harmonic bundle. Then IB, IC. Yeah, but this wouldn't work. Okay, let me get rid of that for now. So I could try this. If I draw an AC and AB, then I prove, like in my video on the Symedian theorem, these points are collinear with P, and the segment is anti-parallel to BC. So maybe that could help. So M, I think M is M the orthocenter? No. So the antipode of A is the orthocenter of this triangle. I don't know if that's helpful for this problem though. You know what? I'm going to try to use this circle right here. So what if I draw, because we want to show this is a right angle, right? So maybe I could use this point right here. I want to show KIE equals 90. Maybe I could show KNE is 90 or KDE is 90. Is that true that L, O, and H are collinear? That would be interesting. It looks like it's true. Looks like L, O, and H are collinear. Okay. Interesting. Is that obvious? Well, yeah, because if this was 90, then that would have to be 90, so they'd have to be collinear. So that's not that surprising. Okay, so is there another way? So we showed NIED is cyclic. So yeah, maybe we can redefine this whole thing. Yeah, so NIED is cyclic. And then we have like another point K that lies on it. How do we define? Yeah. Is F the orthocenter of AK now? Redefine F as the intersection of NE and the perpendicular from I to AM. Okay. So I think I'll just hide this circle right here. How is F defined in the problem? The circle with diameter BC. Okay, so okay. And define IF intersect MH intersect. It's all right. Are you sure we don't know? Maybe we could use the radical axis theorem to show it exists. So like we have the perpendicular, so we know that this is cyclic. And oh, we'd have to show IFBC is cyclic. Yeah. It's already 11:53. Time flies. Yeah, we haven't used that angle BFC as 90. I think that's an issue. We need to use that angle BFC as 90. So BFC is 90, and we want to show FIE is 90. Is FIE similar to FBC? I would be surprised, but it's possible. No, they can't be similar. This is so tricky. I need to use something about E. Yeah, there's a lot of information that we just haven't used. We need to use something about point E. And I think you said it earlier that EDIN is cyclic. But yeah, once we know EDIN is cyclic, we don't really need all this, right? So wait, D is defined. We kind of do because we know how to define B. Then F is where BC intersects EN, and E. Okay. Yeah, it depends how we define I. Yeah, it looks like we do need the circle because that's part of how we define I. Interesting. This is a tricky problem. Let's check.
We want to show that EN and EA are isogonal in BEC. That is equivalent to the problem.
Okay.
Because we can finish after that with isogonal line, power ratio lemma.
Okay. I think we just want to show EM and EN are isogonal.
EA and EN are isogonal in BEC.
EA and EN?
Yes.
I mean, that's the same as showing that EM and EH are isogonal, right?
Yeah.
That doesn't seem like it should be too bad. Although I don't know. But so AP is a symmedian. Okay, hold on a sec. So OB and OC are tangents to the circle. And so EO, let's see. How does this work? EO is a symmedian, basically, because OB and OC are tangents, right? So EO and EB are isogonal. And not only that, we have so yeah, not only that, PM and PC are tangents. So I'm thinking about this circle right here. Okay, so EO, I know we're out of time. I'm just going to think for a minute on this. So EO and ED should be isogonal. And we want to show EM and EH are isogonal. All right, I think we're pretty close. If that solves it, let me check this. Is this actually a right angle? I don't think it is. No. That seems like it has to be doable. Let me think for just one more second. So you're thinking maybe the isogonal line lemma. Can we use? So ED is the median, and so EO and ED are isogonal. We need to show EH and EM are isogonal, but D and M. Yeah. So yeah, we'll see if we can finish this after the session. But this is a fun one. I really like that first problem a lot. So thank you all for sticking around and participating in the session. I feel like we had a really good one today. That problem especially that problem with Monge's theorem, we didn't solve it, but yeah, I'm really curious if any of you end up figuring it out. So for all of you watching on YouTube, if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we will meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.